First of all, this was inspired by 2 interactions with customers in the past 1 year. Folks wanted to build a brand new greenfield networks based on the old stuff. Old stuff is classic TE, right? This immediately triggers why questions, why you want to do it. Thankfully, they decided to pivot to something that is more easy and more robust and more up-to-date. So let's dive into it. I have 30 minutes for about 37 slides. There is a second part to this deck, which was saying, or how to migrate your configurations today. It's still there. I moved those slides in the appendix because I don't think I will have time to just go over those configurations. But there is plenty of them in the current decks as well. That's the agenda. We already passed away the welcome and intro, and we're going to start with some historical context. But before that, I want to start with a definition of chaos by Edward Lawrence. And I acknowledge with this that when we innovate as vendors, as a community, we spread a lot of misinformation, right? And I hope with those few slides, I'm going to clear the air for you. So let's dive in. The historical piece. For me, it started with ATM. Right? When I joined that company, when we were talking about ATM, the senior engineers back then were saying, "Oh, another terrible mistake." Right? I never figured out why another, but the terrible mistake, you all know why, right? Probably is the sale tax, 37%. Probably the expensive hardware. But the idea we got from the ATM, we wanted to put it into IP networks. Like, we had a massive IP community back then, growing this day towards ATM. But what they love in ATM was the circuit-oriented nature, connected-oriented as well, and we wanted to bring that into the IP networks. Back in the days, I've met a lot of you doing traffic engineering in IP, by tuning metrics, admin distances, different protocols, and leaking between them. It was really hard, you know? There are many people claiming today that they can do it at scale, but eventually they mostly gave up. The next thing we did was MPLS traffic engineering. It solved the problem of IP, TE, the scale of it, but it came with its own problems. And most of the telcos in the world, they implemented it slightly to achieve fast reroute. That was the 90% of the cases. I have a slide about it later. And some tactical traffic engineering. And by tactical traffic engineering, understand explicit paths around problems. Really easy. So the challenges that MPLS traffic engineering or the classic traffic engineering brought to us is the scale. So we had a high head-end scale, high midpoint scale, and eventually if you want to grow that network beyond something, you need to uplift everything. So this is expensive. So the core device scale, I have the formula there, but most of you know that if you do full mesh, things in the core get really nasty. And again, you don't get to do inter-domain steering and stuff like that. You got to bring another protocol to help you, which is BGP-LE. So when we wanted to solve something, we didn't simplify, we just throw another protocol in it. Probably most of you are doing it today. So let's see the new way, or the new stuff, right? So till now, if you're still RSVPT, that's all right. I will expect you to start thinking about moving after this, those few slides. So this is SR-MPLS. Segment routing has 2 data planes. One of them is the MPLS data plane, and the other one is IPv6. We're going to see it later. It's a bit of a spicy slide that follows. I intentionally left it as it is, but let's see the SR-MPLS first. It's simple. It goes with IGP. You know, everything you do it in the IGP, and things are fine. No tunnels, no fancy knobs. Well, we have the fancy knobs now, but if you want to keep it simple, you can. It offers you multi-domain, so if you're using PCE, you can do multi-domain steering. You don't need to do, well, in the SR-MPLS, the BGP-LE is still there, but at least you can do multi-domain steering with a little bit bigger brain on the side. Like RSVPT and SR-MPLS, they tend to be distributed. So many small brains around the network. What SRMPLS doesn't have is the bloat in the midpoints. The scale is gone. The state is in the packet. That is what you get. So you configure on the head end, and that's it. There is no state anywhere kept in the network. This comes with a lot of questions about RSVP-minded guys of how we're going to do out to bandwidth. I have a slide for you later. But pretty much with SRMPLS, we're removing 2 protocols from the network. Like, this is the first time for many years we're not adding, we're removing. Like, LDP is gone, and RSVP is gone. So this is the spicy slide. I'm going to pause for a while just for you to absorb the information. SRv6. It's the same segment routing idea, but this time we're using IPv6 as a data plane. On the second slide, I said that IP traffic engineering is hard. IPv6 traffic engineering is not with SRv6. So we like to remove stuff when we simplify. With SRv6, we remove most of the protocols you have in your network today. And it's a kind of an unexpected innovation because it solves problems in multiple domains. I left VXLAN there intentionally. Today, you can run SRv6 in your data center without VXLAN, achieving the same results. What's even better, you can run SRv6 on your host, and you can ask your application to encode the intent. And it will be the same packet going through the service provider network, through the data center, to the receiving application. Nothing changes. It's an IPv6 packet. So it's simple, really simple. I'll move forward. I can entertain that for about an hour, but I'm going to prefer to do it later. It's really sticky, and it's really nice and beautiful innovation. So if you want to do traffic engineering today, we're using few use cases, and I'm gonna go through them and tell you my vision of how many % of the use cases of your network I can solve with a particular tool. So these will be the segment routing tools, not RSVPT tools. But I'm going to make a comparison between them as well. So in your implementation today, across the globe, 80 to 90% of the RSVP traffic engineering was implemented to achieve one simple outcome, fast reroute. And I agree, you all will agree, it's not an easy task, right? We do, in RSVPT, we have 3 types of different configuration to achieve 3 different outcomes. Next hop, or the link protection, is one configuration. Next hop, or device protection, node protection is a different configuration. Path protection is a completely different thing as well, right? And you gotta be really, really knowledgeable of the network you're building these configurations so you can achieve the right outcome. It is also slow. If you have a big topology, it's really slow to converge. And the things with the scale is getting really crazy and out of whack really fast. I've seen people doing protection by placing the protection link over the primary link. So you don't have a protection. But that's why you gotta know your network. It's pretty complicated. And here is a bit of the configurations you can see. This is the next hop protection. There is a lot of information you gotta know about it, but you can't simply create another tunnel to protect the primary one. You know, you gotta pick a point of local repair, which is usually a core device. Then you gotta merge the old tunnel, the new tunnel with the old one. Then we have a merge point, and you have a protection. Things are getting a little bit crazy with a node protection. As you can see, I changed the topology a bit so I can accommodate another merge point. This is a node protection, and here's how it looks. You can achieve all this with segment routing by simply enabling TLFA. So, sorry, I have some animations. I think I disabled them, but they're still here. So we gotta click a few times to see them all. In segment routing, this is in the IGP for you. You don't need to do those fast reroute configuration. It's probably 2 lines. It's not probably 2 lines. It's 2 lines in your IGP protocol and you're achieving it. The beauty of it, the post-convergence path that the IGP will come up with, it's the IGP post-convergence path. There won't be any flip-flop of the traffic. So when there is a failure, we go to the backup path and we don't go back anymore. It's done. With fast reroute in RSVP, you're going to flip-flop the traffic. This comes with one more benefit. The algorithm, the IGP algorithm today, supports something we call micro-loop avoidance. Let me go through the animation again. I don't think I have time to just go step by step. Sorry. Micro-loop avoidance will make sure that if there is a possibility of any micro-loop on the post-convergence path, we're gonna ensure that the traffic is pinned in a way that you will never experience any micro-loop. This provides you with a very stable and predictable network. There is no such a thing in RSVPT today. And there is no way to achieve it. Here is the config. So I'm being a nice guy, giving you the OSPF and RSIS. If you come to me and ask me which protocol should I use, I'm going to vouch for RSIS. But there is 3 lines in this configuration that enables TLFA and micro-loop avoidance. Let's talk about the other tools we have in segment routing. So I'm going to use this pie chart to tell you how much of the use cases I can solve with any tool, any of those tools. But I think my personal opinion is that the flexible algorithm, I can solve 80 to 90% of your use cases today. It's a bit hard, right? It's the key building block. The beauty of this key building block is no matter what you do, no matter how you do it, it's going to end up. I've heard people saying about the maximum seed depth or label depth. This tool gives you 2 seeds. Right? That's it. You can do, I would have said that this is 90% for sure if we're talking about SRv6, but due to the SRMPLS and the label scale of the boxes we have today, we'll say 80. Right? 80% of your use cases today can be solved with Flex Algo. It's that good. And the beauty, again, it's 2 seeds. So we don't discuss the seed depth at all here. The other thing is it's a native steering. You don't need to do any fancy steering to pin the paths, to add it into the routing table. It's there. If you configure it, we have something called on-demand next hop. It will catch it and steer the traffic through the proper policy. It's easy. I have a slide for you as well later. But this tool, 80% of your use cases. I have this percentage below, so you can see I'm going to count to 100 now. And here is the Flex Algo toolbox. If you want to be nerdy, if you want all the knobs, they're there. So you can go crazy. So a simple Flex Algo with intent, whether it's metric, delay, it can be any metric, generic metric. You can come with a metric. Maybe electricity power is a metric for you as well. Can solve the problem for you. Here is how it looks to configure it. It's really easy. Sorry, it's really easy. I'm using Affinity in this configuration to configure a flexible algorithm. And you can see that the path on the top, it's only 2 labels. The only thing you have to do is on the egress side, set up a color community. It's a BGP extended community. Everything that is colored with this particular community, in my case is 100, it's going to go to FlexAlgo 128, and it's going to be only 2 seeds. So when I say anything, just any service, any packet. It's that easy. Let's go to the next one. So, because I'm going to be showing some SR policy in the next few slides, we got to just define what an SR policy it is. There is no tunnels in segment routing, neither in segment routing v6. It's just SR policy, and they kind of play the role of tunnels, if you want to think like an RSVPT guy. So the tunnel, or the policy, is configured with caller and endpoint. Of course, we configure them on the head end. which means that we have a headend, caller, and endpoint, and this triplet has to be unique between any two headend endpoints. Apart from that, that's how the policy looks like. I have a better explanation of the policy later, but when you see it, it has a preferences, the high preference win. In this case, the preference 200 is an explicit path. I intentionally left it to be explicit path because I believe this is most of the use cases you do with RSVPT today. So let's talk about explicit path next. I'm going to make an assumption, which I know it's bad, but I'm assuming 90% of you guys are using explicit path in your configurations. You know, you can come to me after that and correct me if I'm wrong, but this is the biggest tool from RSVPT world today, explicit paths. We're using them from everything. And here's the config. You have a tunnel, you have explicit path, and everything is fine. You can specify protection. This is, I didn't show you how you do path protection, but this is how we do path protection in the Cisco world. And that's it. That's explicit path. In the segment routing and segment routing v6 world, explicit paths will be 5 to 10% of your use cases. If you follow my guidance to use FlexAlgo, you're going to use explicit paths only when you need to explicitly specify loose or strict SID lists. Maybe a little bit of manual tactical TE, where you want to go around the problem in your network. And that's it. That's where they finish. There is another use case with explicit path. We're going to see it later. But using them freely everywhere won't be that widespread if you use FlexAlgo properly. Here is how explicit path looks like. We have a policy. We have a caller of that policy, an XHop. We're calling, the name of this type of policy is on-demand next hop because we're specifying the endpoint. And we have a binding SID. You can leave your device to come up with a binding SID, or you can configure it manually. This is kind of a special SID for BGP, and you can expand it later. But I don't have time to talk about it for those use cases, unfortunately. This particular policy, we're going to use preference 200. Higher the number, higher the preference, and it's the explicit path, and we have a SID list. So you can do labels, you can do IP addresses, same as RSVPT, right? It's still the MPLS data plane. And this is the preference in the policy. It defines two paths. One of them is the explicit path, and the other one is, if the explicit path doesn't work, we're going to go to preference 100, lower preference, which in this case is a dynamic, and we're going to use the metric, traffic engineering metric. So you can go crazy. I show you all those knobs are there. You can do the crazy stuff again, but a little bit more simpler than before. We don't have the states. I'll try to remind you a few times that we don't have the states. So on-demand next hop is what we're going to talk about next. This is the next use case, and I kind of combine it with the disjoint. Disjoint is an important one. Disjoint use case is an important one because it might be creating a new revenue stream for all of you. So what is an ODN? It's the headend automatically instantiate an SR policy based on a template you configure. So you can say, you can tell the device, if there is something that comes with a color of blue, go this way. If it's a color of green, go this way. And you don't need to specify anything anymore. The device will do it for you. We can combine this with automatic steering. If you want to specify the next hop, we can do it. And for those who likes to think about like RSVP and looking at the routing tables, we can place this in the routing tables. Right? You can see when you show IP route, you can see that there is a SR policy in there which points to something. Easy. What you can do with this one is you can do per flow steering as well. So if you want to send your TS1 traffic in one direction, TS2 traffic in different direction, you can do it in a single policy. We call that per flow policy. It's really powerful, but I haven't seen it used a lot. You can do different things with it, and the use case is really powerful. And there is nothing like this in RSVP today. you got to do separate tunnels in RSVP. So I've mentioned automated steering. I don't have an example for automated steering. It's just you specify the template. In the template, you specify the endpoint as well, and you're achieving an automated steering. So you don't need to steer the traffic. The traffic will be automated steering. Here is how the template looks like. We have two colors, 10 and 20. We specify on the ingress of the traffic how we want to tag it, with which color. And once we do it, the device, the head end, will automatically instantiate that policy and route the traffic the way you specify in the policy. So it's a really simple one. As an example I'm showing, it's IGP and latency. If you're color 10, you're going to go to the shortest path. If you're color 20, we're going to use the low latency path. It's really easy. Right? We're using BGP to color the traffic, and then the policy to steer it. There is no other knobs you can use there. Of course there are, but you don't need it. That's the result. So I mentioned that disjointness is an important use case as well, and it is because telcos around the world is using it as a revenue-generating service, right? So with RSVPT, to create a disjoint network, you have to specify two explicit paths to make sure that they don't cross each other anywhere in the network, and protect the primary with the backup, right? That's the case, and you got to configure it. With segment routing today, considering what we're talking about the same head end and same tail end, we can do it on the device without configuring any SID list, explicit paths, or anything like that. It's that easy. So we also support in segment routing disjoint paths between different head ends and tail ends. For this, we're going to need a bigger brain. The distributed brain of the network won't help us, so we need a PCE, we're calling it a policy computation element, that will do the math for us. In the end of the day, traffic engineering is a math problem, and it's a hard one. That's why we have so many flavors of it. So if you have a PCE, you can ask the PCE to compute the disjoint paths between two different head ends and tail ends. Without it, we can do different disjoint paths between the same head end and same tail end. Here is the config. It's a bit more involved in terms of typing, but when you look at it, it makes a lot of sense. The way we're doing it, we're doing two policies, and both policies we specify the same group ID, and we ask them to do no disjoints. What this will result is two different paths, which are completely disjoint. They don't cross each other. So this policy is a service for one of your customers who asks for a disjoint, two disjoint paths. Easy, right? You don't call anyone to tell you which routers you got to cross. The network will do that for you. So with that, I kind of finish with the simple use cases, and I got to move to those. I guess there's some of you who are expecting the advanced one. The first of the advanced use cases is the guaranteed bandwidth or circuit style segment routing. So this is where we involve the bandwidth world in the policies. So we're going to ask the policy to reserve some bandwidth for us. And this is where it gets complicated. I anticipate this to be 2% of the use cases around the world. You can add a PLE if the device is capable of doing PLE into the circuit style. So here, we'll need to advertise the total reservable bandwidth in IGP. Here, we're going to need a controller. You're going to notice that I'm using SDN controller. There is a product names behind it, but being true to the spirit of AusNOG, it's an SDN controller. That will monitor the bandwidth usage. We're doing it through telemetry. You can do it as well. You don't need to get our controller or anyone. You can do your own. And we're going to constantly pull those counters. We also need an admission control, and we also need something to tell us the reserved bandwidth of 10 gigabits. It's 10 gigabits. You got to police it at the end. So we're using QoS for that. That's pretty much the circuit style. You can do it with a controller, and if you want to reserve bandwidth, you can do circuit style without a controller, but if you want to reserve bandwidth, you're going to need the controller to tell you how much bandwidth you can reserve. So here is the bandwidth idea and what you can do with your network if you want to reserve bandwidth. You can slice your network into circuit style slice, into IP slice, and you make sure that you're putting the circuit style services in the circuit style slice by placing them in, for example, CS7 QoS bucket. And if you can remember something from this slide, is to don't commit what you don't have. This is not like RSVP. If you commit more, we're going to give it, but you should not do that. Here is how a manual circuit style SR policy looks like. The idea of it is the path I route to you must be the same path you're going to route back to me. In segment routing, we have a notion of not protected SIT and protected SIT. For this one, we're going to use unprotected SIT because we're specifying a protection path after that. And this use case is done, right? It's pretty much easy to solve. What the complexity here it is you got to deal with a controller that will pull those counters for you and tell you how much bandwidth you have, how much bandwidth you're using, and how much you can stretch. There is a lot more configuration in this deck. I put them in the appendix, as I said in the beginning. So you can download it after that and just have it with you. If you need something more specific as a configuration, I didn't have time to put everything in. Just ping me, and I'm going to provide you those configurations as well. Here is how it looks, the procedure looks with a bandwidth reservation when we have an SDN controller involved. It's a lot of API calls to make it work, but it's working today. So this use case goes into another one, bandwidth optimization. We're using the same tools. I'm going to mention it later. But once you have those policy compute elements and the SDN controller in place, there is no limit of what you can do. You can start pulling the devices. You can start doing if-then. What's going to happen if I lose this device? But we have a tool for that as well. So the next one, I'm not going to say the last one, but it's for those who are really, really RSVPT-minded folks, right? You guess it, out to bandwidth. So this is a really hard problem to solve in SR-MPLS due to the fact that we can't scale those counters that fast, and we can't pull them that fast, right? Because MPLS has a counter, every LDP, every FEC has a counter, too many counters. But we still have a solution for it. If you want to talk about it, come to me. I'm going to tell you what the solution it is. It uses the very same components we saw before, but it's hard. We expect this to be 1% of you. At least I expect you to be 1% of you, those who are using RSVP out of bandwidth. Right. This is the tool that we use in RSVP in trying to solve the distributed brain problem, right? But it is capable of such a meltdowns that you're going to wake up at 2 a.m. You're going to wake up your colleagues as well, so you can cry together, right? It's really, really bad when the things go bad. And this is about SR-MPLS. Like SRv6 is a bit different. We can solve it easier there because we have the scale of IP. We don't have labels. We don't have facts. It's a different story. But the last use case is probably something you guys do on a daily basis. You know, tactical traffic engineering or bandwidth optimization. Or basically say, I want this traffic from A to go through C and not through D, because there is a congestion somewhere. You can automate that, or you can do it manually. If you have the SDN controller can do it for you. In SRv6, we have the notion of deterministic demand matrix. What this is we pull all the counters very fast, and we have perlocated counters to build that matrix on which we can base our decisions later. And once we have the matrix, we have another use case, which is the capacity planning, which is not available at RSVPT. So what this capacity planning gives you is the ability to simulate multiple what-ifs. And this is the last slide I have. The other two are just the fillers, if I had enough time to just fill it with them. But thank you.